On July 17, 2001, the Italian National Institute of Geophysics and Volcanology issued an urgent alert that would capture the attention of the entire world. Mount Etna, Europe's tallest and most active volcano, had begun a major eruption that would go on to become the most significant volcanic event in Sicily in over a decade. But this wasn't just another eruption in Etna's long and violent history. This was the first major volcanic eruption of the 21st century, and it would fundamentally change how scientists monitor, document, and respond to volcanic activity across the globe. But how exactly did an eruption that initially seemed like typical Etna behavior escalate into a months-long crisis that threatened thousands of lives and millions of dollars in infrastructure? What made the 2001 eruption different from the countless eruptions that came before it? And why do volcanologists today still refer to Etna 2001 as the benchmark that divided old-world volcano monitoring from the modern era? Watch closely, because what happened on the slopes of Mount Etna in the summer of 2001 wasn't just about lava and ash. It was about humanity's first real-time confrontation with a major volcanic event in the age of digital technology, satellite monitoring, and 24-hour global news coverage. July 12, 2001. Scientists at the INGV Etna Observatory in Catania, Sicily, had been monitoring unusual seismic activity beneath the volcano for several days. The mountain, which stands at 10,922 feet above sea level and dominates the eastern coast of Sicily, had been relatively quiet since its last significant eruption in 1993. However, the seismographs were now recording something different. A swarm of small earthquakes, each measuring between magnitude 2.0 and 3.5, was clustering beneath the volcano's southeastern crater. The ground deformation instruments, which use GPS and tilt meters to detect even millimeter-scale changes in the mountain's shape, showed that Etna was inflating. Magma was rising. For the researchers who had spent years studying Etna's behavior, these signs were unmistakable. The volcano was waking up. But what they couldn't have known at the time was that this awakening would mark the beginning of the most comprehensively documented volcanic eruption in human history up to that point. The meteorological and geological setup around Mount Etna in mid-July 2001 was textbook perfect for a major eruption. Beneath the volcano's surface, a massive chamber of molten rock had been accumulating for years, fed by the ongoing subduction of the African tectonic plate beneath the Eurasian plate. This geological pressure cooker had been building slowly and steadily, and by early July, the magma had found its pathway to the surface. On July 17, 2001, at approximately 5:30 a.m. local time, Mount Etna began its eruption. But unlike the explosive, catastrophic eruptions seen at volcanoes like Mount St. Helens or Pinatubo, Etna's awakening was more gradual yet equally dramatic. A fracture opened along the volcano's southern flank at an elevation of about 8,200 feet, creating what volcanologists call a lateral vent. Within minutes, fountains of incandescent lava began shooting 300 feet into the air, illuminating the pre-dawn sky with an otherworldly orange glow. News crews who had been on standby after the seismic warnings rushed to capture the event. Helicopter footage from that morning shows rivers of molten rock cascading down the mountainside at temperatures exceeding 2,000 degrees Fahrenheit. The lava flows, glowing bright orange against the dark volcanic slopes, moved at speeds of up to 15 miles per hour in some sections, consuming everything in their path. "We've got massive lava fountaining occurring right now on the south flank of Etna," one volcanologist reported to Italian television that morning. "This is developing into a significant eruptive episode. We're monitoring multiple vents, and the situation is evolving rapidly." By midday on July 17th, 3 separate fissures had opened on the southern and southeastern flanks of the volcano, each producing its own lava flow. The flows were heading directly toward the Piano Provenzano tourist complex on the northern side, and threatening the town of Nicolosi to the south, home to approximately 8 residents. But the lava wasn't the only threat. Massive plumes of volcanic ash began rising from the summit craters, reaching heights of over 15,000 feet and drifting eastward over the Mediterranean Sea. What made this eruption particularly remarkable wasn't just its intensity, it was the fact that for the first time in history, scientists had an unprecedented array of monitoring tools capturing every moment in real time. The 2001 eruption of Mount Etna represented a quantum leap in volcanic monitoring technology. While previous eruptions throughout the 20th century had been documented with film cameras, written observations, and basic seismographs, Etna 2001 was being captured by an arsenal of cutting-edge instruments that would have seemed like science fiction just a decade earlier. Satellite imagery played a pivotal role for the first time in volcanic crisis management. NASA's Terra satellite, launched only a year prior in December 1999, carried the Aster thermal imaging instrument capable of detecting heat signatures from space with unprecedented precision. Every few hours, as Terra passed over Sicily, it captured infrared images showing the exact temperature, size, and movement of each lava flow. Scientists could now track the eruption from 438 miles above Earth's surface, seeing patterns and behaviors invisible from the ground. The INGV had also deployed a network of over 30 GPS stations around Etna's flanks, each continuously measuring ground deformation down to the millimeter. As magma pushed upward and laterally through the volcano's interior, these stations recorded the mountain literally swelling and shifting in real time. When combined with data from electronic tilt meters buried in the volcanic slopes, researchers could create three-dimensional models of where magma was moving beneath the surface. Thermal cameras positioned at strategic locations around the volcano recorded every explosive burst and lava fountain in infrared, revealing details about eruption dynamics that visible light cameras simply couldn't capture. Meanwhile, newly deployed spectrometers analyzed the chemical composition of volcanic gases being released, measuring sulfur dioxide emissions that reached over 30,000 tons per day at the eruption's peak. But perhaps most revolutionary was the internet connectivity that allowed this data to be shared globally in near real time. Volcanologists in Japan, the United States, and across Europe could access the same monitoring data as their colleagues in Catania, collaborating and analyzing the eruption as it unfolded. For the first time, a major volcanic event was becoming a truly global scientific effort, watched and studied by thousands of researchers simultaneously. As the eruption intensified through late July and into August 2001, the threats to surrounding communities grew exponentially. The lava flows, which had initially seemed manageable, began to diverge into multiple branches, creating a complex network of molten rivers that defied early predictions about their trajectory. By July 19th, just 2 days after the eruption began, lava had advanced over 3 miles from the initial fissure, destroying a section of the provincial road and cutting off access to several mountain villages. The town of Nicolosi, perched on Etna's southern flank at an elevation of 2,300 feet, became ground zero for evacuation efforts. Local authorities, working in coordination with the Italian Civil Protection Department, began ordering residents to leave their homes as lava flows inched closer to the town's outskirts. "We are evacuating approximately 1,000 people from the areas most at risk," announced Sicily's regional president during a press conference on July 20th. "The situation is evolving hour by hour, and we cannot take any chances with people's lives." But the lava wasn't the only crisis. Catania Fontana Rossa Airport, one of Sicily's busiest airports located just 18 miles south of the volcano, was forced to shut down repeatedly as massive ash plumes drifted over the facility. The volcanic ash, composed of tiny fragments of pulverized rock and glass, posed a severe threat to aircraft engines. Between July 17th and July 23rd, the airport closed 5 separate times, stranding thousands of tourists during the peak summer travel season and causing an estimated 50 million euros in economic losses. The Piano Provenzana ski resort and tourist complex on Etna's northern slope faced complete destruction. Lava flows measuring over 30 feet high overwhelmed the facility on July 19th, consuming chairlifts, restaurants, hotels, and parking lots. Video footage from that day shows glowing lava engulfing buildings as tourists and staff members watched helplessly from a safe distance. The complex, which had been a major tourist attraction and economic driver for the region, was reduced to rubble and solidified rock within hours. Roads buckled under the heat, power lines melted, Water supplies were contaminated with ash. The eruption was no longer just a geological event, it had become a full-scale humanitarian and economic disaster. As the crisis deepened, Italian authorities made a controversial decision that would spark intense debate within the volcanology community. They would attempt to divert the lava flows using controlled explosions and earthen barriers, a technique that had been tried with limited success during previous Etna eruptions in 1983 and 1992. But in 2001, with improved technology and real-time satellite monitoring guiding their efforts, officials believed they had a better chance of success. On July 27th, Italian military engineers working alongside INGV scientists began constructing massive earthen barriers and channels designed to redirect lava flows away from inhabited areas. Bulldozers and excavators worked around the clock in the scorching heat, pushing volcanic soil and rock into walls that stood over 30 feet high in some sections. The goal was to create artificial channels that would guide the lava toward unpopulated valleys and away from Nicolosi and other threatened towns. Simultaneously, Italian Air Force helicopters began water bombing operations on the leading edges of lava flows. Each helicopter could carry approximately 1,000 gallons of water, which was dropped directly onto the molten rock in an attempt to cool and solidify it, creating natural dams that would slow or redirect the advance. The operations, conducted in extremely hazardous conditions with helicopters flying through ash-laden air and intense radiant heat, represented one of the most ambitious lava diversion efforts ever attempted. "We are using every tool at our disposal," explained one civil protection official during a televised update on August 1st. The helicopter operations alone have dropped over 8 million gallons of water on the lava flows. We're also monitoring the situation minute by minute with satellite data, which allows us to adjust our strategy in real time based on how the lava is behaving. The efforts showed mixed results. Some barriers successfully redirected smaller lava flows, buying precious time for evacuations and protecting critical infrastructure like water treatment facilities and power substations. However, the main lava flows, some measuring over 60 feet wide and 40 feet deep, proved too massive and too hot to be significantly altered by human intervention. The sheer volume of molten rock, estimated at over 60 million cubic meters throughout the eruption, simply overwhelmed many of the engineered defenses. By mid-August 2001, after nearly a month of relentless volcanic activity, the eruption finally began to show signs of weakening. The lava fountaining that had reached heights of over 300 feet in late July gradually diminished. The effusion rate, which measures how much lava is being expelled per second, dropped from a peak of approximately 50 cubic meters per second to less than 10. Seismic activity beneath the volcano decreased significantly, and the GPS stations recorded that Etna's flanks had stopped inflating and had actually begun to deflate slightly as the magma chamber emptied. On August 9th, the last major lava flow came to a halt approximately 2 miles from Nicolosi's town center. The town had been spared by a combination of natural topography, the diversion efforts, and perhaps a bit of luck. While the Piano Provenzana complex was completely destroyed and sections of provincial roads were buried under 40 feet of solidified lava, no lives were lost beyond the initial evacuation phase. The eruption had caused an estimated 100 million euros in damages, but the human toll could have been catastrophically worse. The final phase of the eruption extended into early October, though activity during this period was limited to minor gas emissions and small lava flows from the summit craters. By October 15, 2001, the INGV officially declared the eruption over. Mount Etna had been actively erupting for nearly 3 months, making it one of the longest sustained eruptions in the volcano's modern history. In the aftermath, teams of scientists descended on the volcano to conduct detailed surveys of the newly formed lava fields. What they discovered was remarkable. The eruption had produced 7 distinct lava flow fields covering a total area of approximately 7 square kilometers. In some places, the new lava was over 100 feet thick, completely reshaping the volcano's topography. Chemical analysis of the erupted material revealed that the magma had come from depths exceeding 6 miles beneath the surface, providing valuable insights into Etna's complex plumbing system. But perhaps most importantly, The wealth of data collected during the eruption, from satellite imagery to ground-based measurements to gas chemistry samples, represented the most comprehensive data set ever assembled for a single volcanic event. Scientists now had a complete picture of how a major basaltic eruption unfolds, from the first seismic tremors to the final wisps of volcanic gas. So what made the 2001 eruption of Mount Etna truly different from every volcanic event that came before it? The answer lies not in the eruption's power, not in its duration, and not even in the destruction it caused. The difference lies in how this single event fundamentally transformed volcanic science, crisis management, and public engagement with natural disasters for the entire 21st century. The Etna 2001 eruption established protocols and methodologies that are now considered standard practice at volcano observatories on every continent. The integration of satellite thermal imaging, GPS deformation networks, real-time seismic monitoring, gas emission analysis, and ground-based visual surveillance into a unified early warning system proved beyond any doubt that volcanic crises could be managed proactively rather than reactively. Before 2001, these technologies existed independently, but Etna demonstrated how they could work together as a cohesive monitoring framework. Volcanoes from Kilauea in Hawaii to Eyjafjallajökull in Iceland to Mount Merapi in Indonesia now employ the same multi-sensor approach that was pioneered and perfected during those 3 critical months in Sicily. The data collected during the eruption led to over 200 peer-reviewed scientific papers published in the years that followed, covering everything from magma ascent rates to lava flow modeling to crisis communication strategies. Researchers discovered that by combining satellite thermal data with ground-based measurements, they could predict lava flow paths with unprecedented accuracy, sometimes forecasting where flows would travel up to 48 hours in advance. This predictive capability has since been applied to eruptions worldwide, saving countless lives and billions of dollars in property. The eruption also marked a revolutionary turning point in how volcanic events were communicated to the public and the media. For the first time in history, eruption updates were posted online in real time, accessible to anyone with an internet connection anywhere in the world. The INGV's website, which had previously received a few hundred visits per day, suddenly logged over 2 million visits during the height of the crisis. News organizations could embed live webcam feeds showing the eruption as it happened, bringing the raw power of a volcanic event into living rooms across the globe. Scientists could share preliminary data and collaborate across continents within minutes rather than weeks. This unprecedented transparency not only improved public safety through better-informed evacuation decisions, but it also engaged millions of people worldwide in understanding volcanic processes, creating a new generation of citizen scientists, volcano enthusiasts, and science communicators. Perhaps most significantly for global volcanic hazard mitigation, Etna 2001 demonstrated that modern monitoring technology could save lives without requiring the enormous infrastructure investments that had previously been thought necessary. The lessons learned were quickly applied to volcanic monitoring systems in developing nations, where the majority of the world's most dangerous and most populated volcanic regions are located. The techniques tested and validated at Etna, from affordable thermal satellite imaging to low-cost seismic networks to community-based observation programs, became the blueprint for volcano monitoring in places like the Philippines, Indonesia, Central America, and East Africa, regions where millions of people live in the direct shadow of active volcanoes. But there's something almost poetic about the timing of this eruption. Mount Etna, which had been erupting periodically for over 500,000 years, chose the first year of the new millennium to show humanity exactly how far volcanic science had advanced and simultaneously how far it still needed to go. The eruption served as both a validation of decades of research and technological development and a humbling reminder of nature's raw, unpredictable power that no amount of human ingenuity can fully control or contain. Today, when volcanologists, emergency managers, and disaster response coordinators reference modern volcano monitoring, they're almost always referring to the post-Etna 2001 era. The eruption didn't just mark the beginning of a new century. It marked the beginning of a new age in how humanity observes, understands, and responds to one of Earth's most powerful and beautiful natural phenomena. What's your opinion on how this eruption changed volcanic science? Let us know in the comments below.